This is the first telescope. It was used by Galileo Galilei in the year 1609 to discover the 4 largest moons of Jupiter and prove for the first time that the Earth was not the center of the universe. And this is the James Webb Telescope. It was launched into space in the year 2021 and is used to investigate distant galaxies, the Big Bang, and the true origins of the universe as we know it. Over the 400 years that separates these two designs, the evolution of the telescope has been driven by our own insatiable curiosity about what lies out there beyond the stars. The true origins of the telescope are a bit fuzzy, but we know that it all began in the Netherlands in the early 1600s with a Dutch eyeglass maker named Hans Lippershey. He was experimenting with this idea of stacking different kinds of lenses on top of each other to create a magnifying effect. His invention was incredibly simple. You have 2 glass lenses set inside a wooden tube. The lens at the front of the tube is convex, meaning that it curves outward. Light rays enter the lens traveling in parallel lines, and then the curvature of the lens starts to bend those lines towards the center until they all converge at a single point. That is called refraction. If you've ever used a magnifying glass to concentrate sunlight into a small point where it gets hot enough to start a fire, well, that's exactly what the first lens in our telescope is doing. Now, the magic of this design comes when you add the second lens at the back of the tube. That is the eyepiece. This lens is concave, meaning it's curved inwards. And to make this telescope work, you need to position the eyepiece at the location where all of the light rays from the front lens converge into a single point. And when the light hits that back lens, the curve is going to straighten all of those lines back out again. So our first lens is collecting the light and squeezing it down. Then our second lens is grabbing that light and stretching it way out to project a much bigger image into your eyeball. That's how a telescope works. Those early Dutch telescopes were able to create around 3 times magnification, which was useful for spotting ships out at sea, but you weren't looking deep into outer space. That is where Galileo comes in. He was a pretty smart guy who lived in Italy from 1564 to 1642, and he's generally regarded as the father of modern science as we know it. But his most significant work was in the field of astronomy. It's the thing that ended up getting him in big trouble with the Catholic Church and ultimately resulted in him dying in captivity. In the year 1609, Galileo started hearing about what the Dutch were up to with their magnifying tubes, and without ever seeing one of the original designs, Galileo had managed to build his own version in just a few days. Only Galileo's telescope was able to achieve 20 times magnification. While the Dutch guys like Hans had just been messing around with common eyeglasses, Galileo had the luxury of selecting larger and higher quality pieces of glass and then grinding his lenses very carefully to precise curvatures. And when Galileo pointed his lens towards the night sky for the first time, he started making some pretty incredible discoveries. When he looked to the moon, Galileo was stunned. He could see clearly that it was covered with mountains and craters. This was already starting to break from the established knowledge of the universe that was set down by the philosopher Aristotle in the 3rd century BC. He said that the sun and the moon were perfect spheres composed of a celestial material he called ether. But now, Galileo was looking at the surface of the moon with his own eyes, and he could see that it was actually just a big rock covered in mountains and valleys. It was rough and uneven, just like the surface of the Earth. You know, when we talk about humanity's journey into space, we're really talking about how fragile and extraordinary our existence is, and that's exactly the feeling captured in a book I've been diving into lately. The last book, The Diary of the Last Earthling from Hungry Minds. It's not your typical book. It's this fascinating hybrid, part diary, part encyclopedia, written from the perspective of Noah Kaplan, the last surviving human who escapes Earth's destruction on an alien ship. To fight the loneliness, he writes down everything remarkable about humanity, our achievements, our art, our daily lives, things like how we first started to fly and our progression to sending rockets to space. What I love about it is how it blends emotional storytelling with real science and history, all wrapped up in stunning illustrations and premium design. It feels like both a cultural time capsule and a collectible piece of art. Honestly, flipping through it is like holding humanity's story in your hands. If you're someone who appreciates space, science, or just the wonder of being human, I think you'll find this book as inspiring as I did. It also makes a really meaningful gift for anyone who loves beautiful, thoughtful books. You can check the last book out for yourself. Just follow the link in the description and use my promo code SPACERACE for 10% off, available for 1 month only. So that must have been a pretty mind-blowing revelation. But then Galileo started looking even deeper into space. He pointed his telescope at Jupiter. And while he still didn't have enough magnification to actually see the planet in detail, he was able to recognize that there were 4 smaller points of light that surrounded the large planet. And as he continued to observe those 4 lights over several days and weeks, he realized that they were satellites orbiting around the planet Jupiter, just like our own moon circles around the Earth. This discovery was even crazier still, because Aristotle had already decided that the Earth was the center of the universe and all other celestial bodies revolved around it. And since this was the prevailing theory around the time of Jesus Christ, it ended up getting written into the Bible, and it essentially became a religious belief that the Earth was the center of the universe. But now, Galileo was thinking to himself, if these smaller bodies are in fact circling around Jupiter, then it must be true in the universe that smaller objects tend to revolve around bigger ones, which would mean that the moon revolves around the Earth. But then it also has to mean that Earth itself revolves around the sun. This led Galileo to a new theory of his own, that the sun was actually the center of the universe and everything revolved around it. So he still wasn't totally correct, but he had gotten a lot closer to the truth than anyone had come before. And the Catholic Church did not like that very much, because that's not what the Bible said, and this eventually culminated in Galileo being brought in front of the Roman Inquisition, basically the Supreme Court, where he was found, quote, vehemently suspect of heresy. The result was that Galileo would spend the final decade of his life under house arrest, where he was still able to write books and invent new forms of science, but his social life took a pretty big hit. After seeing what happened to Galileo, it's not surprising that his fellow astronomers were reluctant to agree with the sun-centric model. It wasn't until Sir Isaac Newton came along in the 1680s with his theory of gravity that the true nature of the solar system was generally accepted by the scientific community. Speaking of Isaac Newton, he also had his own ideas about building telescopes. Newton had an idea to use mirrors instead of glass lenses, and this gave birth to the reflective telescope. Again, we start with a wooden tube, except this one is wide open at the front, and down in the bottom of the tube, we are going to put our mirror. Now this also needs to be curved slightly like a shallow bowl. The curve is going to allow our mirror to function just like the convex lens. It's going to focus all of the light rays down into one point in the middle, and that is where we put our secondary mirror. This one is flat on its surface and is typically set on a diagonal angle, so that it bounces the focus light into the side of the tube. That is where the eyepiece is set, and just like in the reflective telescope, the eyepiece has a concave glass element that will take the concentrated light from the mirror and stretch it out into a large image that gets projected into the viewer's eyeball. The advantage to a reflective style telescope is mainly in lower cost and better ease of use. Making a really wide glass lens is really hard, and even if you could make such a lens, it would then be incredibly heavy, so that's just not practical. Meanwhile, making a curved mirror isn't anywhere near as difficult, and the end result will be pretty light. So the reflective telescope made astronomy accessible, and it also allowed designers to make extremely wide telescopes. The wider your mirror, the more light it will collect, and that makes it possible to start seeing things that are invisible to the naked eye, like distant stars and galaxies. Throughout the 1700s and 1800s, engineers continued to develop both the refractive and reflective telescope design. While reflective telescopes are more practical to build, they do suffer some problems with image quality, mostly because you have that secondary mirror sitting in the middle of the tube. It breaks up the light and reduces the overall clarity of the image. This is where refractive telescopes maintain an edge. their glass lenses achieve the highest level of sharpness and contrast, allowing astronomers to see details of planets and moons in our own solar system. Unfortunately, there is a hard limit of what is possible with glass lenses. The Yerkes Observatory in Williams Bay, Wisconsin is home to the largest refracting telescope ever built. It was completed in 1897 and has a primary lens that is 40 inches or 1 meter in diameter. That lens alone weighs 225 kilograms or 500 pounds. The telescope is considered to be a masterpiece of late 19th century engineering. Nothing like it has even been attempted since, and probably never will be again. This should give you a pretty good indication why mirror-based reflective telescopes ultimately won out. The largest telescope built in the 1800s was known as the Leviathan of Parsonstown. It was located in Ireland and it featured a 72-inch or 1.83 meter wide primary mirror. The tube itself was 56 feet long and it was mounted between two 40-foot stone walls. The movement of the telescope was controlled by a series of chains, ropes, and pulleys that allowed the operators to easily point it anywhere in the sky. With this telescope, we were able to clearly see the spiral structures of other galaxies for the first time, like the Whirlpool Galaxy and the Crab Nebula. Now, they didn't know exactly what they were seeing at the time. The general consensus was that these must be large clouds of dust that have taken on interesting shapes. But the idea was beginning to emerge that they might just be island universes, meaning the clouds might be both incredibly large and incredibly far away, and they aren't made of dust, they are made of stars. This is where modern astronomy as we know it was really born, in the early 1900s with a group of astronomers in California who start to combine observation with the scientific method. You might recognize this guy among them, Edwin Hubble. And this crew begins to integrate giant telescopes with laboratory facilities, hence the observatory. The Mount Wilson Observatory is located in the mountains north of Los Angeles, and in 1917, they complete work on one of the most important telescopes in history, the 100-inch reflector. It would hold the title of largest telescope in the world for the next 3 decades, and in that time, some of the most important astronomical discoveries are made, particularly from our friend Edwin Hubble. In 1923, Hubble started pointing his telescope at a giant gas cloud known as the Andromeda Nebula, and he noticed something really interesting. He was able to spot a very unique type of star inside the cloud. It's called a Cepheid variable, and they're special because they tend to pulse from bright to dim in a regular repeating pattern that happens relatively fast over the course of days or weeks. The star itself actually gets bigger and smaller, so by measuring the speed of that pulse, astronomers can figure out the actual brightness of the star. Basically, the slower the pulse, the brighter the star. So what Hubble knew from taking the pulse of this star was that it must be incredibly bright wherever it is in space, but through his telescope it appeared to be incredibly dim, which means that it must be incredibly far away. The conclusion that Hubble drew from this was that Andromeda couldn't possibly be a simple cloud. It was a gigantic system of stars, and it was so far away that it had to be completely separate from our own system of stars. This was the first proof for the island universes, which would come to be known as galaxies. Andromeda is the closest galaxy to our own, so it was the easiest to spot. But once Hubble locked in the method for identifying these things, he started finding a lot more. There were galaxies in every direction. The true scale of the universe was starting to come together, but there was one more big discovery to be made. Because Hubble also noticed that all of these galaxies were moving, and they were moving away from us, meaning that the universe is not stationary, and it doesn't move as one cluster, so it must actually be expanding outward. And if the universe is currently expanding, that means at one time, all of these galaxies must have been closer together. So Hubble didn't invent the Big Bang Theory, that was Georges Lemaitre, but Hubble's ability to prove universe expansion is what gave credibility to the Big Bang and solidified that as our leading theory for the origin of the universe. From here, the evolution of the telescope continued in 2 directions. Of course, one was size, wider is better, and eventually the 100-inch reflector was replaced by the 200-inch reflector, and so on. But there was also a revolution in the scientific instruments that you were able to integrate with these telescopes. Now we start to see light beyond the ability of the human eye. These laboratory inventions allow for the detection of ultraviolet and infrared light, plus much more complicated things like radio waves and microwaves. The general design of the reflective telescope remains the same, but the technology that supports these observations grows exponentially with the dawn of the computer age until we eventually begin to reach the limits of what an Earth-based telescope can do. So we take the next logical step. We go to space. Let's talk about the reasons why you might want to launch a telescope into space, because it's not about getting closer to the planets and stars, it's actually about getting further away from the Earth. Because for all of the advancements that have been made over the centuries, a telescope is just a tube that collects light. And as technology revolutionized human civilization, the Earth itself started generating a lot more light, which in turn creates interference that makes it harder to see the fine details of the distant universe. To break free of these limitations, NASA invents the first ever space-based telescope, and they name it after our old friend, Hubble. Largely because the big opportunity with a space telescope is to pick up where Hubble and his generation of astronomers left off, to see deeper into the universe than would ever be possible from the ground. Now, there are pros and cons to a space-based telescope. One of the biggest cons is that Hubble needed to fit inside the space shuttle cargo bay, which was pretty big relative to the size of a satellite, but it was actually pretty small for a telescope. So the width of Hubble's main reflecting mirror is limited to 7.8 feet or 2.4 meters, smaller than the telescope used by the real Mr. Hubble decades before. But what it lacked in size, the space telescope made up for in technology, using digital cameras that could pick up light far beyond our own eyes. Here's how that looks in very simple terms. Light travels in waves, and those waves exist on a spectrum from very high frequency to very low frequency. The part of that spectrum that's visible to us is kind of right in the middle. In the higher frequencies above visible light is ultraviolet, and in the lower frequencies below what's visible is infrared. Hubble can see everything in the visible spectrum, but it can also see all of the ultraviolet light, and it can see some of the infrared light, what we call near infrared. And this is important because as light travels through the universe, the waves get stretched out. So what begins as high-frequency UV light from a star over billions of years becomes low-frequency waves of infrared. So in order to see the oldest light in the universe, to basically see into the deep past, you need to get access to those infrared frequencies. And that is very difficult to do from the surface of the Earth because there's too much interference from all of the heat and light. So the Hubble Space Telescope was able to accomplish two very important things. One was to create all of these beautiful images of the most amazing locations in the Milky Way and all of the nearby galaxies. But the second, and arguably most important, was to start investigating the origins of the universe. And it was through these observations that we were finally able to put an age to the universe. Astronomers determined that the time between now and the Big Bang was 13.8 billion years. They also discovered evidence for dark energy and dark matter, which is the invisible force that is believed to drive the expansion of the universe. And Hubble found that nearly every major galaxy, including our own, revolves around a supermassive black hole at its center. These observations provided a foundation for everything we think we know about the origins of the universe. But at the same time, we know that we aren't getting the full story. We know that Hubble is only touching the infrared spectrum, but it can't go any deeper because from where it's located, there is still too much interference coming from the sun. So what we need is a telescope that doesn't just orbit the Earth, but actually hides in the Earth's shadow, where it can collect the oldest and deepest infrared light in the universe. This is what drove NASA to create the James Webb Space Telescope, an evolution of Hubble that would be able to overcome many of those previous limitations. While the James Webb and Hubble might look incredibly different, the biggest change is not so much in the design, but in the location where they operate. While Hubble orbits the Earth at an altitude that's a little bit higher than the ISS, NASA placed James Webb 1 million miles away from Earth, far beyond the Moon at a location called the L2 Lagrange point. This is a place where the gravity of the Earth and the Moon kind of balance out, so you can put an object on a Lagrange point and it won't get pulled into orbit of the Earth or the Moon, but it will follow along with them as they move through the solar system. It's basically like a space parking spot. And if you park something at the L2 point, then you know it's always going to be in the shadow of the Earth as it moves around the sun. That alone is going to block out a lot of the sun's infrared interference. But then James Webb also has a 7-layer sun shield to put itself even deeper into the dark. So on the other side of the shield, you don't even need to put a tube around the two mirrors of the telescope because there's no light left to block out. And that allowed NASA to do something very special with the main reflective mirror on James Webb. They made this folding design of hexagon tiles that allowed the mirror to fit inside the relatively small cargo bay of a rocket when it was launched into space. But then, once it arrived at L2, the mirror could expand out to a width of 6.5 meters or 21 feet across. Now, the size of this mirror is rivaling the biggest telescopes on Earth, but it has all of the advantages of being shrouded in total darkness at all times. And that is why NASA has been using James Webb primarily to conduct infrared astronomy. This telescope is seeing the universe in a way that was never possible before. It's getting a clear look at some of the oldest light in the universe, taking us all the way back to what was happening just after the Big Bang, if there even was a Big Bang. The trick with James Webb is that its vision is so unique that we are only just beginning to understand what it's showing us. We are not really getting answers yet, just more questions. But that's good. That's the way this process has always gone. The telescope is only a tool that reveals possibilities. Then human curiosity and the scientific method does the rest.